Hi everybody, couple of notes about symmetries on the unit circle. Here's what I mean by symmetries. So right here in red, we've got the height at the angle 5 pi over 6. So the sine of 5 pi over 6 is that y coordinate. You see that exact same value at a whole bunch of other places on the unit circle. So here, however, you also see it as a horizontal distance up here. You would also see it as a horizontal distance down here. So the fact that you can see that same value in several places, and you can kind of see their symmetries, like this is a reflection across this way. This would be a reflection around the line y equals x. Means that you can start writing things like sine of 5 pi over 6 is the same thing as sine of pi over 6. That's the same thing as cosine of pi over 3, which is the one up here. And it's cosine because we're looking at the x coordinate at that particular point. That would be the same thing as the cosine at the point down here, which is negative pi over 3. It's the same angle, just in the opposite direction. So negative pi over 3. Okay, well that by itself maybe is not so interesting. But we can start to generalize. Like let's pretend these are all an angle theta, where we don't necessarily know what that height is. Like maybe this is a height of 1/10 or something. So we don't know a special angle that will give you a y coordinate of 1/10. However, you can still write these same ideas. So here, I'd have sine of theta is referring now to that red one. How would I refer to that red height? Well, it looks like it would be sine of, let's see, halfway around, and then I'm subtracting the angle theta. Here, I'm rotating by an angle theta starting at 0 this direction. Here, I'd be rotating at an angle of theta, but I'd be rotating backwards, so it would be opposite theta. And I'm starting at pi. So you could think about that as pi minus theta. Up here, you could think about this as starting at 90 degrees, which is pi over 2 radians. And again, I'm rotating the opposite direction, so I'd have pi over 2 minus theta. What about the one down there? We could have, I guess let's think about it as, I'm trying to decide, should I do 3 pi over 2? No, yeah, all right, let's do that. So 3 pi over 2. And then, am I going plus theta or minus theta? It looks like I'm still continuing around this same counterclockwise direction, so that would be plus theta. So the reason to write all of these things is maybe you have something that looks like this in an equation, but you'd like to rewrite it just in terms of simple input. So I can rewrite something like this just as being sine theta, and that might simplify my algebra to some extent. There are other places where it's useful as well. So in class, I had the students think through these ones, but let's just do them together. We're going to decide, is each one true or false? So I'm going to kind of sketch a picture for each. I'm going to start with deciding the angle. Where is it located on the circle? So if I have this as angle x, the angle at opposite x would be here. And then if I'm finding cosine, cosine is the horizontal distance. Sorry, it's not the horizontal distance. This is going to be really important in a second. It is the x-coordinate of those points. So you can see the x-coordinate of this point is that. The x-coordinate of this point is the same. So this one is true. This one is going to seem very similar. Let's draw the same picture. So here I've got an angle of x. Here I've got an angle of opposite x. But here we're looking at the y-coordinates. So the y-coordinate of the first one is this. The y-coordinate of the second one is that. They kind of look the same. I mean, they're the same sort of size. They're the same length. But this is not equal. And the reason they're not equal is because this one is a positive y-coordinate. And this one is a negative y-coordinate. However, we can fix it quite easily. We could just say, let's write the exact same thing, except I'm going to leave a little space to the left of sine here. So that's the same statement. What we know is that the numbers on both sides are the same value. It's just that one is positive and one is negative. Like imagine that x was pi over 6, in that case, on the right-hand side, sine x, this would be positive 1/2. On the left-hand side, sine opposite x, it would be negative 1/2. So to make them the same, let's just flip the sign of one of them. So there's a couple of these that you just want to know, just have memorized. These are two of the ones that you just want to have memorized. Let's do another one. So here I've got pi over 2 minus x. So pi over 2 is straight up. And if I'm going to subtract x, that would be the angle in that direction. Is that the same as sine of the same angle x, but rotated up this direction? That's what we just talked about up here, actually. So it's sort of symmetric around this line, y equals x. And you can see that that distance and this distance should be the same. They're the same length. This is a positive y coordinate. That's a positive x coordinate. So they're also the same sign. So this one is true. This is another really important one to know. Let's write in another one. The same would be true if I'd said sine of pi over 2 minus x equals cosine x. And the reason why is if you imagine the height here is the same as the horizontal x-coordinate there. So y-coordinate here, same as x-coordinate there. So the ones that are highlighted, let's do the last one. So the ones that are highlighted, those are four that you should just know. You should just recognize. When you see cosine pi over 2 minus x, you should think, oh, right, it's like the reflection. Okay, sine x. Let's do one more. Cosine pi over 2 is straight up. If I'm going to then add an angle x, that takes me to here, and I'm looking at cosine, which is the x-coordinate, is that the same thing as sine x? Sine x would be here. So similar situation, it's like the distances are the same, but this is a positive y-coordinate, and that's a negative x-coordinate. So if we wanted to fix it, so this is false, if we wanted to fix it, we could say cosine pi over 2 plus x equals opposite sine x. So this isn't one that you see a lot. These are kind of the main ones that you see a lot and you might want to replace. But if you were to see one like this, remember, you don't have to be completely stuck like there's nothing you can do. You can think about what is this actually describing about coordinates on a unit circle, and you can rewrite it just by thinking on the unit circle. Okay, let's do last part of the notes. So I believed that you'd been taught this last year, but apparently not. If you have any function at all that satisfies this description, it's called an even function. So this description, you could think about it in terms of transformations. So let's say f of x is a graph. And then equals means is the same. And then this is the same function, except it's been reflected horizontally. So the graph of f of x is the same as its own horizontal reflection. All right, so we can imagine a couple of examples of this. One would be cosine x. Let's just imagine the cosine x graph for a second. If you were going to imagine reflecting this around the y-axis, you can see that the graph is going to end up being the same. So it's a great even function. What are some other functions? X squared would be an even function. So would x to the 4th. So would x to the 100th. Because they all have this horizontal reflection symmetry. What else? Absolute value x is one that the students brought up. So all of those are great even functions. Okay, there's so many typos here, we just have to scrabble everything out. So what would be an example? So these are even functions. They're odd functions. What's an example of an odd function? You could write it two ways. You could say f of x equals opposite f opposite x, like this. Or you could do it this way. Opposite f of x equals f opposite x. it's not two totally different things. Like imagine taking that top equation, multiply both sides by -1, and now you get this equation. If I'm going to describe the top one using transformations, f is the same if you reflect it. Think about what reflections are happening here. We've got a horizontal reflection and a vertical reflection. So f is the same if you reflect it horizontally and vertically. All right, let's look at what that might look like. If I've got sine x, let's do a careful sketch of sine x. Let's go in both directions. So first I'm going to reflect it one way, then I'm going to reflect it the other way so that we can kind of see what happens. I'm going to put this point up here as a point that we can track. So let's first reflect it horizontally, okay? So if I reflect it horizontally, this ends up here, like that. Okay, now let's reflect it vertically. So that point ends up down here. Okay, so what I want you to notice is this graph is the same as this graph. This point ended up in a different spot. This point, after you reflected it here and then down, ended up down here. But every point on the graph here ends up on a point on the graph here. And each point here corresponds to a point up there. It's the same points, it's just that they all got mapped to different places. So, same graph. What are some other examples of odd functions? Oh, let me point one more thing out. So you could think about it geometrically as reflect horizontally, then reflect vertically. Imagine that I had instead taken the graph and then rotated it 180 degrees around the origin. So this point would have rotated around here, that point would have rotated around there. 180 degree rotation around the origin is just the same thing as those two reflections. So you could think about it that way as well. And if you're thinking about it that way, pretty clearly x cubed has that exact same symmetry. You could imagine rotating it 180 degrees around the origin. Okay, that's it for the notes. Come back next time.